Right. So my name is Jianqiao Mao from University of Birmingham. I'm doing my PhD with Max Little. So this is my final year PhD study, and my research mainly focuses on the causal machine learning. So today I will give a talk about my research. So the title is about from observation to intervention. We'll introduce some causal sampling methods and some applications in the machine learning. So I'm not quite sure that what you guys' backgrounds from. So, but just to give a very quick introduction about the causation and the differences between them. So for like hundreds of years ago, like Hart person believed that the causation is just ultimate scientific illusions of so everything can be just described with a contingency table, or just every analysis can be done with a correlation. Correlation is sufficient for all the analysis. But so to Pearson, the correlation is just another fetish should miss the inscrutable arena of modern science. This as a result, that mainstream statistics went far away from causal analysis for decades, and that actually leads to the consequences that most of the modern machine learning models are purely data driven and learning the causation, the correlation instead of the causations. But if we think about everything is about correlation, there is some funny stories, for example, as shown in the screen. If you consider about the two variables, one is total revenue generated by the arcades, and another one is the computer science stock rates of voting in the US every year. So if you just use one of the variable to predict another, you probably get very nice accuracies and very small errors for prediction, because the two variables in this 10 years are highly correlated. But that's just probably because of some coincidence that two variables get highly correlated. And this kind of correlation is somehow spurious and it's not reliable. If you just deploy the model using one variable to predict another one, the model probably fails in the next year. So this is not a reliable and a causal model that we can rely on. So in some critical fields, for example, in the medical finance, then it's very hard to trust this kind of models that's totally blind to a causation. But as we have also seen recently, for the example, ChatGPT or the large language models, like also a lot of deep learning models, are very powerful for a lot of tasks. But does this kind of powerful refer to a human level intelligence, which means it can capture a causal relationship between the variable, or just the animal-like abilities that can capture regulations between the variables, which just captures the correlation. So in Pearl's opinion, who built up the building of the causation, in his opinion, that bringing causal knowledge into a current machine learning model might be the key to open the door to a strong AI or general AI. Because in his opinion, like the association is the first layer of the knowledge that is only need to be can answer the question such like what if something happened, and I see what outcomes. But in the second layer and third layer, that's for the causal stuff. One is we call intervention. In this layer, if we can do intervention, that means we can answer questions. What if I do something, and what will happen in the next? And in the counterfactual, that's higher layer. Then in this layer, we can actually doing like the human abilities, like imagine and also understanding and explain the reason. So standing on the top of the causal ladder, AI may get a chance to have the so-called cognitive revolution. So this is probably more practical examples, which is the brightness means the problem. That means in the data set A, that is a confounded data set where the digit category is confounded by the background's brightness. So as you can see, the digit 2, averagely speaking, is darker than the digit 6. And for example, if you get this data as your training data and you train the model, then, well, what you can expect is that your model probably learns the background, the average brightness of your image instead of the actual shape of the hat right digit. But that's just not what we expect. And also, we don't want the model just learns this kind of overview, spot, bias features. Then if you really train a model on this confounded data set A, then test your model on some applications. For example, you get test data in the B, then you probably get your model performance very bad because in the data set B, then the background brightness is randomized, and the model probably just decides which digit the image belongs to, just based on the background brightness, but not the shape of the digit. So that's actually what happened in a lot of the machine learning applications nowadays, if we don't care about the causation. Because your observational data can be confounded, and the confounder probably is not overused as example showing the mixed data sets. It's probably very hidden and very difficult to find out. Then you just use a confounded data train a model, then your model gets naturally biased in a lot of test scenario. So these two figures actually compares the traditional and the causal machine learning while it can be done in different applications. For example, the traditional machine learning, you just try to learn the PY given X and T, which is T the treatment in this case. Like for example, we're predicting some patient survival scores. And if you give the treatment or not give the treatment, you just get a single outcomes. Or what we expect for the causal machine learning can do is we think about for given X and Y, if we intervene on the treatment, that means if we give the treatment or we don't give the treatment, we can get different outcomes based on the causal knowledge that we have known from the data. But these are kind of fundamental challenges for machine learning model if we want to enforce them to learn the causal knowledge. Because most of the non-confounded data are actually collected from the well-controlled experimental environments. But environmental data is not always available and easy to obtain. For example, if you want to obtain the experimental data for the weather, that's almost impossible. You cannot intervene the weather to be sunny or to a rainy day. You can only get observational data in these cases. So the question naturally turns out is that how to train a causal-aware machine learning model using the confounded observational data when the control experiments are difficult or even impossible to conduct. So our idea is that can we still use the observational confounded data and try to apply some causal sampling techniques and to get a deconfounded data set that's approximate to the non-confounded experimental data distribution. Then you use the deconfounded data for all the downstream applications, for example, the causal machine learning training, or you want to estimate the treatment effects and also extra. So the core of this technique is actually how we design the causal sampler that can generate the deconfounded data, which has a distribution close to the non-confounded interventional distribution. But before we go further on the techniques, probably let's consider a scenario that is a little bit different from traditional causal inference. So the causal inference is what we know that we want to, for example, infer the effects from the causes. That's the traditional way is to, for example, estimate the intervention distribution Px given do Y, or try to estimate the treatment effects if we intervene on Y. But what we consider for the reverse causal inference, you want to actually infer the causes from the effects. And actually that's how the supervised learning model is used and applied for a lot of medical applications. For example, for the disease diagnosis, the Y can be some disease categories or the diagnosis. And the X can be some like observations, for example, the CT scans or the medical signals that we observe, which normally is high dimensional one. So of course, that's the category of the disease should be the causes, and through some mechanism of this disease, and you have the observations for the medical data. In this case, when you train a model, use X to predict Y, what you're doing using your supervised learning model is reverse causal inference. That is, infer the causes from the effects. So there's a important technique which is trying to embed the intervention distribution into a weights, which we call causal weights. But generally speaking, for any graphical structure causal model, we cannot guarantee that every graphical model and the causal effects of interest is identifiable, but the do calculus give out the intervention distribution expression as Formula 1 gives out, but only if the causal effects of interest is identifiable. But for example, the graph A and B, which are two typical backdoor and front door confounding scenarios, they are definitely identifiable. But in more general cases, like for example, the graph C shows is not necessarily identifiable. But if it is, then we always have the intervention distribution can be expressed in this way. So with the expression 1, then let's think about the joint distribution of Px and all the other variables in this term, first term of the expression. Let's consider about joint distribution. Then we can replace it by a kernel density estimator. So with the products of all the kernels and sum them up, which is equation 2. Then if you insert the equation 2 to 1, you get you can rewrite the equation 1 into the expression 3, the formula 3. Then now you can think about that we kind of changes the original joint intervention distribution into replace the joint one with some kernels. And because a variable set epsilon are actually something that we are not interested, so we can just simply try to marginalize it out. But if you want to calculate the actual expression for this formula 4, that is very difficult because you want to do an integral. You may don't have the closed form. But if you use a Tonelli's theorem, you can actually interchange the sum and the integration. And now you got formula 5, and let's deal with the integration now. So to deal with the integration, thanks to the kernel function, we have the reproducing properties. So actually we can rewrite, let's take the second part out and consider this part as a weights, because the first part of this expression is just the bootstrapping kernel, right? And because of the reproducing property actually of the kernel, so we choose from the reproducing kernel Hilbert spaces, then we can actually replace all the integer with the kernel products with the distribution with the evaluation at each data point we have. So now we actually somehow remove the integers and replace it with the evaluation at certain data points. And then actually, so this expression 8 gives out a weights expression for every data point from your observational data sets. Then that's actually also embedded the causal knowledge and the causal structure for every sample that you have. Then when you want to do some resamples using the weights, you can just given an interventional value, y, then you can get a set of the weights and you do the resampling, weighted resampling, then you can get a data set, a new data set which approximates to a non-confounded data set, because the weights naturally embedded the causal structure and knowledge. So a very simple method that you can apply with causal weights is actually we call it causal bootstrapping. With the weights, for example, you have the original data, then you calculate the weights for a given intervention level. Then some of the data set, some of the data will have larger weights, and some of them will have less weights because of by computation. And you just bootstrap them and relabel them with intervention level. And you change your intervention level to the next classes, for example, your discrete Y. Then you repeat the procedure again and get the new data sets and relabel them with the intervention level. And you repeat until you literate all the intervention level that you want. Then you get a set of a new data set, which we call the confounded data set, resampled by according to the weights and also relabeled with the intervention level. Then you get the data set you want to use to train a model, and enables the model to learn the causal knowledge. So this actually demonstrates some results over here. So I told you examples with synthetic data. In this figure A, actually this is a confounded data set, and there is the existence of the confounder, which is represented by the orange line, leads to a shifted distribution where the class 1 intended to distribute it over the right upper corner, and the blue dots, which are class -1, intended to concentrate on the right lower corners. So the results of the mixture of the confounder and the true class boundaries leads to, if you train a linear support vector machine, then you will get a decision boundary with also a mixture of the two boundaries. But if you consider, like, if there is no confounding effects, that means there's no any confounders between Y and X, then if you generate the data set, you can find out actually the trend linear SVM have a decision boundary which is close to a true class boundary. That's what we expect. But if we use a causal bootstrapping on the confounded data and resample it, and you get a new data set, like we call the confounded data set. And if you train a new model on this resample data, you actually get a deconfounded decision boundaries, which is also close to the true class boundaries, and eliminate the confounders effects to the model. So that's actually shows how this works to the actual observational confounded data, and help us to train a model which learns the causal relationship between the variable. But as you can see, the bootstrapping method is very simple, and just repeat the same data point in your original data set. You cannot get some new informations, and you even somehow losses information because you do the resampling, and some of the old data set probably have with a small value of the weights that you cannot get the sample again in your new data set. So that's somehow like if you have a model if you have data in a very high dimensional space, then you use a causal bootstrapping, then you probably get a model, your data with limited diversity, then your model probably easily gets underfitted. So a improvement for the causal bootstrapping, that we can consider some more advanced samplers, for example, the Gaussian mixture models, but causally weighted version. So it's also very simple. We just integrate the causal weights into the M step. That's all the statistics here are a weighted version comparing to the simple Gaussian mixture model fitting process. So for example, for the coefficients of every component or Gaussian components, for the mean and for the covariance are all causally weighted using the causal weights we have computed in the above. So let's check about how it performs. So the first column is actually the non-confounded distribution for the level Y equals -1 and Y equals 1. So that's actually the ground truth. We can think about that. But this distribution is estimated from the KDU. So if you choose different components of the Gaussian, the different number of the Gaussian components, then you can see that it's somehow approximate to the non-confounded distribution using the originally confounded data. So, but all the two methods are all based on the weights, right? Or based on our observation in the research, like the causal weights, almost because it's ratio construction. So and on the in the denominator you have a probability. Then when it's close to zero, so you have a distribution of your weights very extremely, sometimes very long term. So all of these techniques are based on the weights, which are somehow yearly distribution. So we want to find out some way that we don't rely on the causal weights, but instead directly sampling from the intervention distribution. One way is that we can consider using the hybrid block-Gibby sampling with the MCMC sampling techniques. So if we think about we want to sample from this distribution, which is the intervention distribution that given in the Formula 1, it's very difficult because the expression here you probably cannot find out its closed form. So you cannot compute the probability value densities from this expression. But comparably, if we consider about the joint intervention distribution, there's no integers. So probably it's easier to compute the point densities given all the variables or the data point. So in this way, actually we can consider about using the block-Gibbs. Like let's think about the block-Gibbs samplers aims to sample from a conditional intervention distribution in sequence. That is actually what we real aim is still sampling from the conditional intervention distribution. But because it's very difficult, it has an integer, does not have a closed form, but it has a proportional relationship to the joint distribution. So actually we instead can sample from the joint distribution instead of marginalize out the variables that we really cannot find out the point mass probability to estimate. So with the proportional relationships, we actually can perform the MCMC sampling for those every variable blocks that cannot use a simple for some blocks that with a very simple categorical distribution, we can just simply use a simple sampling method from the CDF stuff. So in this way, we actually skip out the weight computation, and also we only need to evaluate the point density for the joint intervention distribution, and also avoid to compute the integers of complicated expression. But there's also some more advanced way that can be combined with diffusion models. So I'm not quite sure if you are familiar with the diffusion model, but just for a very quick introduction is, so the diffusion model is that for the forward process, it's actually adds the Gaussian noise, standard Gaussian noise at every time steps from the original, for example, image to until it goes to a complete Gaussian noise. Then that's the forward process. And the generative backward process is somehow you denoise at every time step until you recover your image from a noise image. So expression here, you can see for the forward one is just adding the Gaussian noise at every time steps. And the denoise is just the reverse process. But the question here is how can we estimate the noise for the backward process? So we can actually use a deep learning model to predict the noise for every time steps. That's the traditional diffusion models. But how can we use that for the intervention data generation? So because we have intervention distribution as we presented in the previous slides as well, let's assume that only X are high dimensional here. So actually you can easily sample all the other variables from the distribution that you can estimate from your observational data sets. Then you can just actually design a conditional DDPM model where it takes like the embedding of all the conditions of the variable O, which are originally the set of the variable not of interest. So the noise is a conditional one, conditional on all the other variables except for the x, and also interventional variable y, and also the time step t. And you also need input of the image at a certain time step t. So you can train a model, a conditional denoiser, that to predict the noise at a t time step, conditional on all the other variables except for x and y, and to predict the noise at that time step. Then you can do this, for example, using the noise prediction using some deep learning model, such as a UNet or some other methods are always used in the literature, and to do the steps of diffusion. But the only thing is that your distribution of all other variables are conditional on the intervention level one. So you can control actually, for example, for the hand right digit example, you can set your y to digit 2 or to digit 6. Then you generate the deconfounded data sets for digit 2 and digit 6 respectively. So, but that's actually the high level design for the conditional denoiser. But how do you actually embed the causal knowledge into this DDPM model? Is you can just add a loss function, a loss term for the causal consistency. So this loss consistency is actually you take the average, you take the expectation of the generated graph, generated image over the intervention distribution. Well, this is also very hard to be computed because, as we can discuss, the intervention distribution itself is hard to estimate, hard to have a closed form. So what we can do is we can use Monte Carlo estimates to estimate the expectation. Then you involve this expectation of the x over the intervention distribution into the causal consistency loss. Then you actually can embed the causal knowledge into your diffusion generating model. So let's see about the example we have discussed for the background means data. So the data set A is just a confounded data set. As you can see, the digit 6 averagely brighter than the digit 2. And the graph C is originally non-confounded data. So the background brightness is randomized between the digits. But if you use PDPM, that's what we have discussed, that generates the intervention data. And you can see in this case, the background brightness is also somehow randomized. And that means it's eliminated the confounder of the original confounded data. And one of the advantages of DDPM model is that it can generate actually an unlimited number of intervention data than for any downstream applications to train your complicated model or complicated applications or very high dimensional causal effects estimation, because we have, well, theoretically unlimited number of the data you can have. So some applications using the previous introduced techniques, for example, there is one disease called intracranial hemorrhage. Is actually that's how the bleeding happens in your brain. So traditionally, the doctors will try to diagnose your type of your ICH from the CT scans, but it's very time consuming. So the radiologist examination. Nowadays, there are some automatic machine learning assisted methods have been applied and also tested. But most of them, if you only use your CT scans and your levels to train the model, it's most likely to be a confounded model, which can be severely confounded by a lot of factors. For example, the different hospital, different populations of the patients, and different imaging protocols. So your model probably trained on the hospital A's data. If you transfer into hospital B, then probably find your model fails to give out the right prediction and diagnosis. So what we can do on this is we try to use our deconfounding techniques on this data set and to see if we can help on the robustness and reliability of the machine learning. But in the previous setting, then it's too simple. There's only 3 variables. Y is a category is a disease category, and Z is some labeling, some segmentation of the potential bleeding areas, and X is the actual CT scans. So Z is somehow a mechanism that how the, for example, radiologist diagnose which type of the brain bleeding is. So that's represents for the mechanism variable or the mediator of the disease. But there's still very simple causal diagrams. A more practical setting is that we think about the Y is still the category, M is the highlighted injury area, and X is the CT scans. But you also consider some other more practical factors, for example, demographics, and also some imaging protocols, which also perform as a mediator between the type of the disease and the highlighted injury area. And some secondary lesions, if your injury happens, and probably changes your shape of the brain and your shape of the CT scans. So that's also another mediator variable. So that's a more practical causal model for the ICH detection. And using if you try to calculate these causal weights, then you can see it's a very somehow high dimensional expression for you need to estimate the distribution of the high dimensional variables. And then you probably cannot get an accurate estimation for the distribution because of the curse of the dimensionality. So one of the solutions is that can we find out a method to reduce a complicated graph to a well-studied front-door confounding scenario. So in that way, we can reduce the intervention distribution largely, then also you get a simpler expression for the weights. So this is a quick review for the front-door criteria. So the front-door criteria says the mediator variable set M intercepts all the directed paths from X to Y, and also there's no unblocked backdoor paths between X and M, and also all backdoor paths between M and Y are blocked by X. So that is the simplest front-door scenario graph. That means that M is somehow not affected by the confounder directly. But compare this graph with this one. It's still a little bit far away, but let's see, can we simplify it somehow through using the do calculus rules? So there's one of our work has done is to try to reduce the front door, reduce a complicated graph to a standard front door causal graphs. For example, all of this graph in A, B, and C, and D, actually, we can prove that it can be reduced to a 3 supernode settings, which satisfies the front door confounding scenario. But if you directly, for example, in the graph C, if you're using the ideal algorithm, with your standard algorithm to identify the causal relationships, then you get a very complicated expression. But if we can prove that it can be reduced to a 3 supernodes graph, then it can be the intervention distribution expression can be reduced to a very simple, much simpler expression, as shown in 24. So there are a lot of theoretical stuff. I probably need to skip it out. And but if you're interested, you can go further on one of our archive papers for definition of the front door reducibility criterion, and also the front door reducible adjustment expressions. So they are always the mathematical proofs. But let's directly check some examples. For example, we have a lot of complicated causal graphs, like from A to I, but we can actually prove that all of this graph are front door reducible to a simple 3 supernodes standard front door representation. And the X can be, for example, the X, and the Y just simply Y, and you can choose one of them as your mediator set. So with this, actually what we want to do is try to reduce the complicated graph and give a simpler weights expression. Of course, we also have an algorithm that can identify those admissible sets of the variables given the graph. Well, I will not go deep through that. But let's directly, for example, check what we can do for the ICH example. So in the ICH example, the original weights expression, as we can see, is a very high dimensional distribution that you need to estimate. Well, if you reduce it into a standard front door scenario, then your weight expression goes to this. So it's much easier. You only need to consider the variable m and y. You don't need to consider the variable h, s, and d, right? So in this way, it's equivalent, and you can also do the deconfounding. So if you compare like we train a ResNet CNN on the original confounded data and also deconfounded data, but the confounded data, one is generated by the causal bootstrapping, another one is generated by the causally weighted GMMs. Then if you test the data on the non-confounded and confounded data sets, you can see that the confounded model, although performs very well on the confounded data set because that's the same distribution, but if you just transfer into a non-confounded environment, then the model performance just drops like more than 10% of the accuracies. This is what F1 scores, right? So, but it's a significant drop. Then if you consider about the two deconfounded model, let's think about the causally weighted one, causally weighted GMMs one. It performs well and satisfy well, like promising in the confounded one, although it's a little bit lower than the confounded model trained on originally confounded data set. That's of course the best because it's just in the same distribution. But you still get very close, the close performance to the confounded model. But on the non-confounded model, the causally weighted GMM-based deconfounded model gives out a very nice F1 score on this transferred distribution environment. So I think that's actually a very obvious example that say why when doing the deconfounding method that we can maximize the utility of the observational data and also train a model that can learn the causal knowledge, which is more robust because the performance doesn't vary that much as a confounding model did. I think that's all for a little bit rush. So